So Unit 3, Lesson 3, so exponential functions. We're going to kind of talk about exploring exponential functions, how they grow, things to look for, things to notice, look at some graphs, just kind of the full exponential functions entirety of themselves, what we think they're doing or what we notice they're doing, etc. Okay, so let's go through the first thing here. So Mallory, a medical research scientist, discovered a new bacteria culture which could help strengthen a person's immune system. To find the growth rate, she isolated 5 cells of the culture, okay, and observed the following growth pattern. After 1 hour, there are 10. After 2, there's 20. After 3, there was 40. So let T represent the time in hours, and N of T represent the number of cells after T hours. So then it says the formula of N of T as a function T can be written as, so A, B to the T, where A and B are constants, determine the values of A and B. So if you don't know anything about exponential functions, A is kind of your starting amount of cells, B is how they're growing. Okay, so A, starting cells, B, how are they growing? Okay. So we started with 5 cells, so our A is 5, and our cells are doing what? Yeah, they're multiplying by 2 or doubling, so 2. So if you're filling out that exponential function, you're going to fill it out as N of T equals 5 times 2 to the T. Okay, and then so it says use the formula to determine how many cells are there after 8 hours. So where does the 8 go? Goes in for T, right? So you're finding out what is 5 times 2 to the T. So we're doing N of 5. Oops, N of 8, right? Sorry, N of 8 is 5 times 2 to the 8. Okay, if you put that in, you're going to get 1280 for cells. Okay, after 12 hours, there are 2,480 cells. How many hours did it take to have half that amount? It's kind of a tricky question. So, yeah, 11, right? Because we're doubling every time. So to get half of that amount would be the previous hour, right? Because as it's growing, half that amount is always the previous hour. See that pattern? So to get half of that amount there, it would be the 11th hour. Okay, so using graph calculator to graph the function. Okay, so we can do that. Let's go ahead and do that together here. So I'm going to lose my writing here. Let's go ahead and do this, do this, do this, clear, and we are going with 5 times 2 to the x, and graph. And so there's what your exponential function looks like. Okay, things to point out in this. Okay, you can see right here is 5. Okay, that's the start right there. Okay, you can also see that it's taking off very quickly. Okay, so it's going really fast. A couple things to realize, I think it's important to point out, even though you guys probably think it's silly, is that this right here is not realistic because why? Not negative cells, negative time, right? That's negative time. Negative cells is down here, right? Cells is a function of y, right? So yes, there's no negative cells, which is also true, but there's also no such thing as negative time. So that's misleading, okay? So that's really not there. We're going to start from 0 and forward, okay? Your domain would have to be at 0 for time, okay? I don't care how many times you watch Back to the Future. Okay, so then we got, then going back, so you are kind of can sketch that in there. So that's what we just did, that was exponential growth, because the cells are growing. Let's look at decay now, okay? All right, so for decay, I'm not sure what that is. I'm just going to call her Cheryl, Okay, Cheryl's it's a place. Okay, so Cheryl's a city from former Soviet Union. They have some weird names here sometimes, so I was like, I'm not gonna try to do that one. Okay. Chernobyl, is that how you say it? Chernobyl? Oh, Chernobyl. Oh yeah, okay, I've heard that. I've heard of that. Okay, that's good. That's good. All right. So that's a city in Soviet Union, not a person. Okay, good. In April of 1986, there was a nuclear accident, and the atmosphere was contaminated with quantities of a type of radioactive iodine. And at the time of the explosion, the atmosphere was contaminated with 32,768 units of radioactive iodine. The following data was recorded for the dissipation of the radioactive iodine. So after 1 week, there were 16,000. After 2 weeks, 8,000. After 3 weeks, 4,000. And you can see it's essentially it's halving, right? Okay, so the radioactive iodine was decreasing by a half each time. So use t to represent the time in weeks to represent the number of units. Complete the following equation of the function which represents the information provided. So all we have to fill in is 1/2 here, okay? Because it was being halved every time. Now that in the t's weeks now though. Use the formula to determine how many units of radioactive iodine were left after 14 weeks. So that means we're doing 32,768 1/2 to the 14. Okay, and that's going to be 2. So that's almost gone. And let's go ahead and use this, the graph calculator here. Sounds like that's a scale they use, so that's fine. We can use that. So let's go back to my graphing calculator. Let's put it in. So we're going to clear this. We have 32768, 32768 brackets, 1 divided by 2 bracket exponent to the x. Okay, my graph's not going to look very good. I'm going to go change my window. So we're going to change the window to what they have here. So we're going to go window. So they say -1 for min. It says 8 for max. Whoops. There we go. 1 for scale, so we're good there. And then our y is the one that's going to change quite a bit. The y, we're going to go -30,000. 1, 2, 3, 5. Okay, got it. Our max, we're going to go to 64,000. 1, 2, 3. And then our scale, we're going to go by 10,000. One, 2, 3. Okay, and let's see if this turns out. And there you got a much better picture. Okay, so they size that out for you, which is nice. Okay, so you can kind of see a couple things here. Our y is going by 10,000, so you can see that's just above 30,000 because it was 32,768, right? So that's, you can see that's where it starts, and then you can see it's decreasing every time, right? So keep all that stuff in mind. Cool. All right, so let's keep on going here. All right, so exponential function. Exponential function is in the form of y equals a b to the x. A, again, is your starting amount. B is your growth factor if you're talking about exponential. So remember, if it's less than 1, if it's between 0 and 1, you're actually doing a decay. Okay, we've learned about that in Math 20. Okay, so if you have 0 to 1 is going to be decay. So 1/2, 1/3, 1/5, 2/3, 3/4. Those are all going to make your things smaller. Okay, and then anything above 1 will give you a growth. Okay, that's what we're going to compare now. So I kind of spoiler alert. We're going to compare 2 versus 1/2. Okay, say the values of a and b. So say the values. So what's the values of a here for both of them? What's the values for a for both of them? Nope, for this one. There's nothing there. 1. So there's no number there really. So it's just a 1. Okay, so we're starting with 1 in terms of its growth. Okay, and so then we have b. is 2 for this one. B for this one is 1/2. Those are the growths. Okay. Okay, so we're just going to fill out this chart now for 2 to the x. So if I put a 3 in there, a -3, remember with our exponents, that means the exponents have moved down. So it's really 1 over 2 cubed. Do you guys see that? So you push the 2 cubed down because it's 2 to the -3. So it goes to the bottom. So this would be 1/8. And the same thing, 1 over 2 squared would be 1/4. 1 over 2 to the -1 would be 1/2. Anything to the 0 power we know is 1. Okay, and then it's going to go the other way now. It's going to be 2, 4, 8, 16. Okay, so we can kind of see that that's going to be -3, so we'll change this one to green here. So this one's -3 is 1/8, so real small there. 1/4, 1/2, 1, 2, 4, let's see here, 5, 6, 7, 8, and there's no 16 for us here. So here's the 2 to the x. Okay, and now we'll look at the 1/2. Okay, so we put 1/2. Now here's the interesting thing. 1/2, if I put -3 in, that essentially flips it, right? Flips the 1/2 to 2 over 1. So it's 2 cubed, so this is 8. Flips it, 2 squared, 4. What do I mean by flip it? Remember, if this is a negative up here, that I can flip the fraction inside and make it a positive. That's what I'm talking about. So if I flip this, it's 2 over 1, 2 cubed 8. Flip it, 2 squared's 4. Flip it, 2 to the 1's 2. Anything 0 power is 1. And then now it's just 1/2, 1/4. That's a 4 there. 1/8, and then 1/16. Okay, so this one we'll go check out in blue. Okay, so that means we're going to be at -3. We're going to be at 8. Okay, -2, we're going to be at 4. -1, we're going to be at 2. Then we're going to be at 1. Then 1/2, 1/4, 1/8, 1/16, etc. So you see they are pretty symmetric in terms of how they operate. A little curve there, sorry, but you get the idea. Okay, and then we're going to kind of keep that picture in mind. I'm going to have to move up and lose my writing, but we're going to fill out this table here together. Okay, so one thing that I think in general we need to work on from your cubic quiz is our domain and range. So like looking at that picture now, what's the domain of those two functions? What's that? XCR, right? There's no issues of x. As you see, there's no breaks in the graph. I can put any x in I want, and I'm going to get a value. Okay, so that means XCR. Good. What's the range? Y is greater than 0. Okay, and good thing that he just said. He said greater than not equal to, because it's not equal to. We can never get 0, right? No matter what I put into these for exponential growth, I can't get 0, right? So keep that in mind. Those are all good. Good job, guys. Okay, so both of these are XCR. Uh-oh, where'd my toolbar go? Oh, there she is. Okay, XCR, XCR, Y greater than 0, Y greater than 0. Okay, good. Was there any X-intercepts then? No, because Y can't be 0, right? So no, Y can't be 0, there can't be an X-intercept. So that's none, none. The Y-intercepts, they've had the same 1. What was Y-intercept? It was 1. And equations of the asymptotes. So there is an asymptote here that never touches. What is that? 0, right? The Y equals 0 line. Okay, both those graphs up there, they went like this. I'm just going to sketch it here since you already have the picture, but it went like this, and it went like this. It's never crossing that asymptote right there, and that asymptote is Y equals 0 for both of them. Okay, for which one's growth, which one's decay, 2x is a growth. It's doubling. Wow, this is just really not good right now. See if I stand back here. And then 1/2 is dividing by 2, or halving it every time, which is decay. Okay, good. All right. Okay, we're going to explore a little bit more here. We're going to look at a couple more graphs. So we're looking at where A is 1 by using a graph calculator or technology, sketch exponential functions. So you can put those in. I'm going to go ahead and just kind of hand sketch these, but you're welcome to put them in your calculator if you want. But the thing I want you to be able to do automatically after today is that growth or decay? Growth. Exactly, right? So these two are bigger than 1, so they're growth. These two are less than 1, so they're decay. Okay, that's what I want to see. All right, and then they're all going to intersect where? Yeah, they're all going to intersect with that 1 there. So let's use all these colors here. Okay, so let's do this one first here. So 3x, we know it's going to be here. Okay, we can just do a couple. Okay, so 3x, if I put a 1 in, I'm at 3. And if I put a -1, I'm at 1/3. That's good enough for me to draw this, so it's going to look like this. Okay, for the 10x, at 1 it's at 10. So 3, 4, 5, 6, 7, 8, 9, 10 there. And at -1, it's 1/10, right? So you can see it's a big, it's really steep compared to the other one, because 1/10 puts it right here, really close, and that's going to kind of be underneath here a little bit. But it's going to come through here, much higher, and hit like that. So there's your 10 to the x one. 1/3 we know now is coming from the left, coming down to the right. So we know that for this one, it's going to be at 1, it's going to be at 1/3. At -1, it's going to be at 3. If you want another point, you could also do -2, which is going to be at 9, and then 1/9. And so it's going to tail off this way, and it's going to come up this way. Okay, like so. Then the 1/10 is going to be even steeper in the sense of that direction. So -1 is going to be at 10. 1 is going to be at 1/10, and so it's going to be going this way, going that way. Okay, so there's your 4 examples there. So your 2 decays and your 2 growths. Okay, when b is greater than 1, the curve sharply, as b increases, it rises. Between it falls. So what they mean by that is, I know that's kind of how you're looking at it. Whoops. Sorry, I'll switch to black here. Rises, falls. So, you know, rises from left to right, it's going up. Falls from left to right. Okay, that's how they're talking about that. Without using a graphing calculator, make a sketch of the graphs of 5 to the x and 0.2. So we're going to add those. Kind of run out of colors here. Just do these 2 in black. So we know 5 to the x is going to be, again, a riser. Okay, so 1 will be at 5. See right there. And then -1 would be -1/5, so kind of in the middle. So it's going to be here. Whoops. It's going to be more like that, sorry. It's going to be between the blue and the red there. Just ignore that other piece. 0.2x, that's 2/10 or 1/5, so 1/5 should be between these two. Okay, so 0.2, I'll count that as 1/5. I think 1/5 is easier to visualize. So if -1 at 1/5 is at 5, so that's going to be 1, 2, 3, 4, 5, be right there. Still goes through there, and then it's going to be at 1/5. So kind of between those, like that. Okay. All right, so verify the solutions using your graph calculator, so you can do that if you'd like. Just for sake of time, I'm not going to do that part. State the x-intercepts of each of the graphs. So there is no x-intercepts, right? Okay, so for E, just so they all have none. Okay, they all have 1 for the y-intercept. Domain for all of them is XER. The range for all of them is y greater than 0. And the equation of the horizontal asymptote for each of these is y equals 0. Okay, now, so you're seeing like, wow, they're very similar in a lot of ways. What could change a range or a domain here? What could change your horizontal asymptote? What are you having a test on tomorrow? Transformation. So if you move stuff around, it's going to move your restrictions, your domain, and your ranges. Okay, so if I take that exponential and I put a +3 on the end, that's going to move it up 3. So now your horizontal asymptote's now at 3 instead of 0. So that's the stuff we're going to get to. Okay, so understanding that's why we learn transformations first, so that you know that graph's moving. Okay? All right. We good? All right, exploring the value of a to the x. So just looking at now in terms of what's happening in front. Okay, so how that changes. So this is going to change. It's going to change essentially the starting point. So you're going to see this ends up being your y-intercept. Okay, again, I kind of spoiled it, but let's look at it here. So we know that 3 to the x goes through 1. We've already done this one. We already know it goes here, and it does this. That's your 3 to the x. 2 times 3 to the x, we'll now see what happens is if I put a 0 in here, that's 1. 1 times 2 makes me start at 2 now. And so it just stretches it by 2, just like we're used to. Okay, so look what happens at 1. If I put a 1 in there, 3 to the 1 is 3. 3 times 2 is 6. So it's just going up here at 6. So you see it's stretched. Okay, same stuff, and it's just steeper. The 5 times 3x is going to be even steeper. 1, 2, 3, 4, 5 is going to be there. Okay, and then it's going to be 5 times 3, which is 15. That's off the page. So it's going to be doing something like that. And then 0.5 is going to, instead of stretching it, it's going to compress it, or it's going to make it a little bit fatter, if you will. Okay, so this one I'll just change color because it's not stretching anymore. So like these ones were stretches. This one's kind of a compression in the sense that it's getting like wider because it's going to go through right here. And it's going to come through like this, and then it's going to go, one's going to be at 1.5. So it's going to go like this. Okay. Okay, so you can graph this with a graph calculator if you'd like. Okay, we just did them by hand because we have an idea what's going on. Complete the following table for these equations in the form y equals abx. So the value of a for this one, so the value of a for y equals 3x was just 1. The value of a was 2, 5, and 0.5. The value of b for all of them was 3. And the y-intercept for all of them, 1, 2, 5.5. Okay, so what is the effect on the graph by changing the value of a? What does it do? It changes the y-intercept. Good. 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 And it vertically stretches as well because it's making it steeper. Okay. If f of x equals 3 to the x, write the following terms of the function of f. So this is the thing we're practicing with our transformations, right? So this right here is just y equals f of x. Nothing changed, right? It is what that is. This right here is y equals 2 f of x, right? 2 mean the vertical stretch, the stuff we're supposed to know for tomorrow. Okay, this would be the y equals 5 times f of x. And then I'm going to change this to 1/2, just so you can see both. Y equals 1/2 f of x. Vertical stretches, we're used to those. Vertical stretches are what you see in terms of factor, right? The horizontal stretches are the flip. So which transformation? So there's no transformation for I. We don't have to do anything about that one. But 2, okay, so that one has a stretch Vs of 2, Vs of 5, and Vs of 1/2. So what is the effective parameter of A? It's a vertical stretch by the factor of A. And again, there's restating stuff that we've just said. State the y-intercept of each of these graphs. The y-intercept is equal to A. We also did that as well. All right, we're on the decline here. We've got a couple of examples. Okay, a couple of examples. Okay. Characteristics of the graph of the exponential function, f of x equals ab to the x. So the following summarizes the basic characteristics of the graph of exponential functions. So it's kind of putting it all out in our kind of, I don't know, it's like our guided notes here. Okay, the y-intercept is A. There is no x-intercept in this form. The x-axis is a horizontal asymptote. The domain is XER, range is greater than 0. When b is greater than 1, it represents a growth. Okay, when b is between, so we got b, when b is between 0 and 1, it's a decay. When b is bigger than 1, it rises. When b is between 0 and 1, it falls. Okay. When a is greater than 1, the stretch is an expansion. It's expanding out faster. When it's between 0 and 1, it's the compression, as I mentioned earlier. And when a is less than 0, there's also reflection in the reflect when it's so like, yeah, right? This right here, what we're used to, that's an x-axis. Good. Okay, good. All right, let's go through some examples now. We're almost done. All right, examples 1, 2, and then we have 3. We have one more after this one. Describe how the graph of the second function compares to the graph of the first function. So we have y equals 4 to the x versus y equals 2 for the x minus 2. So what do you think? So let's do the easy one. What's the 2 do? Okay, so we have vertical stretch of 2. Okay, what do you think the x minus 2 does? Translation, good. And what kind of which way? Right 2, good. See, you know that because of your test tomorrow. That's your movement with the x, so that's your left and right. Good work. How about b? What do you guys think? So 2 to the x went to, go ahead, let's move that 4 over. Let's just minus the 4 over so we can get rid of that. This is what I was talking about in my text last night. A couple of things on your test tomorrow. Leave stuff with the y, so you just got to move that over to finish that out and get what that movement is, okay? All right, so that's what we have. Negative 2. Okay, now, is the negative part of b or part of a? Sounds like we need to have a vote. Is the negative part, is it a negative 2 your b, or is it negatives the a and 2's the b? Okay, so if you think the negative is a, raise your hand. If you think the negative is a, raise your hand, okay? If you think the negative is part of b, raise your hand. Okay, and then somebody didn't vote. Whistle. You guys are whistles? Okay? That would make it part of B. You have to have the brackets to be B. So it is A. So your A in this case is -1. Your B is 2. Okay, because the negative is not bracketed, so therefore the exponent's only on the 2, not the negative piece. So what this does is, that's a reflection over the x-axis. That negative in front flips it over the x. So we have, okay, well right here, so it's reflect x-axis. We have a 2, okay, so what's the -4 means down 4, right? And what does the x over 5 do? Yep. Nope. What do we do with horizontal stretch? So he's right. It is a 1/5 there, so your horizontal stretch is a 5. Yep. Same rules apply, guys. Right? You see a 1/5. The 1/5, you identified it correctly, but the stretch is the 5. Okay? So reflection on the x-axis. The 2 is what the exponential is doing, but it's not. You're not stretching at all. So that's the original, and then we changed it to the stuff we added here. Yeah. Here we go. And the 2 is not part of a transformation. Yeah. Okay. Explain. What's that? Oh. Explain using transformation why the graph of y equals 1/3 of the x is a reflection in the y-axis of the graph y equals 3 of the x. So this is a good one. This is a good for yesterday. So let me restate the question so you guys are listening. Why? We know that these two graphs look like this. We did it just a second ago. We know the 1/3 does this, and we know the 3x does this, right? So they're a reflection over the y-axis. Why? Good. She's got it. You guys got it. Okay? This can also be written as 3 to the negative x. So having a negative x means reflect over the y. Okay? That's good stuff right there. The diploma type questions are going to ask you. They're going to put stuff that you're not used to seeing. Like they're going to say, what's this reflection? Like they would ask that. 3 to the x is a reflection with 1/3 of x over what? You'd say y-axis. Okay, you have to recognize that this can be a reflection over that because of the negative exponent. Okay, last one. Stay with me. Last one. Here we go. Okay. Consider the function f of x equals 4 to the x plus 2 minus 6. Without using a graph calculator to determine. Okay, so domain and the range of the function. So we got to remember this is what I'm talking about. We moved. So we got to ask ourselves, let's do the range first. What do we do vertically? We move down 6. So my domain is no longer greater than 0. It's greater than. Okay, so range y is greater than 6. -6, yep, sorry. -6, good catch, good catch. Okay? Because it's normally 0, but we move this graph down 6. So now our range is bigger than -6. Okay, so if you think about this, just think if we have an exponential doing this, we move it down 6. It's not doing this. This is now the line that's the range that we're above. Okay, how about the domain? So we moved, x plus 2 means we moved left, right? So if I just take this thing and I move it left, is that changing anything for my domain? No, it's still growing the same thing even though you moved it. So this is still XER. Okay? It's not creating a restriction within your x. Okay? It's not creating a restriction within your x. The y-intercept is the graph of the function, so what's the y-intercept? Well, how do we find y-intercepts general in math? What do? You put 0 in for x. Do that. What's 4 squared? 16. What's 16 minus 6? 10. So that's going to be your y-intercept in terms of that. You just plug in 0, for x to figure out which y-intercept. That doesn't change. What's that? It's because it's going up. Yeah, it's going up. This is the lowest, right? So your y-intercept is 10. How do you get that? 4, 0 plus 2 minus 6. So 4 squared minus 6, 16 minus 6 is how you get the y-intercept. If you're wondering why my picture look close, my picture is a rough sketch. That's not right. Because the reason my sketch is off is because 4 is a pretty big, that's quadrupling every time, so that's growing super fast. So you're looking more at something like this with 4 to the x. You'd have 1, and your first one would be, there's 2 reasons. Actually, let's talk about this. If there was no left or right movement, my y-intercept would be smaller, right? Because if this is just 4 to the x, your y-intercept would still be 1, and then you'd minus a 6 to it, because you'd move it down 6. But what happens is, see this right here? Just to kind of try to picture this for me. Take this, move it left 2, and down 6. See what's going to, this is the guy that's going to hit that intercept now, so it's higher. Does that make sense? So I'll try to illustrate a little bit here. So just think about it this way. We're taking this graph here, we're moving it down 6 and left 2. So if I do that, this guy-ish is going to be kind of right around there, around the 10, because it's growing up so fast to the y-intercept. That's why that's happening. Okay, cool. Last thing, the equation of the asymptotes. So the asymptote now is what? There's no vertical asymptote, it's still horizontal, and where's it at? -6. Good. All right, we're done. Good work.